Hello, my name is Boris Platov, and this is Center for Advanced Training, Quality Management and Marketing, Institute of Geology and Petroleum Technologies, Kazan Federal University. Right now we are going to talk about the structural interpretation. The structural interpretation ends up with the construction of the structural maps. By using these maps, geologists can find the oil traps and investigate the subsurface. Structural interpretation consists of the four main steps. It's seismic to well tie, horizon tracing, velocity modeling, and map calculation. On the previous lectures, we've described what is the seismic to well tie, why and how can we do this. Actually, seismic to well tie is the connection of the wells with the seismic data. In the end of the day, we are obtaining the stratigraphical description of each seismic reflection. And that's how we can find only the one's reflections that is needed for our interpretation. Only the ones which are connected with actual oil and gas accumulations. Horizon tracing is simply the connection of the nearest seismic traces, and it can be done by two different ways. Either it can be done manually or automatically. By using auto trackers, the main idea of the auto trackers is to force the computer to connect the nearest seismic traces to force them to be aligned. In this case, seismic traces simply presented as on the slides, and the computer is simply looking, for example, on that pike, and it is comparing the pike on this seismic trace with the pike of the nearest seismic trace. And if they are similar, automatic auto tracking is simply connecting these 2 points to trace the horizon. Sometimes it's quite simple to trace the horizons, but sometimes it can be quite difficult, especially in case when you got not just a simple horizon layering, but once you get the extinction, once you get a discontinuity of the geological layers. In this case, horizon tracing can be quite complicated. And sometimes the quality of the seismic data is simply not enough to make a good tracing, as it's shown on the figure. Another important question is how to trace a certain horizon. Imagine the situation that you're tracing this positive reflection, this green horizon, and you end up with this point. From that point, there are two ways how to trace the horizon. Either as the yellow line to continue on this line, or to shift it downwards as it's shown with a black line. So which of these two possibilities is correct? The actual answer is no one knows unless you got the drilled well. If you can compare the wells which is on that side from this point and on that side, and if you're comparing the thickness of your layer, and if the thickness is more or less the same, you can say that correct tracing is going there by the yellow line. That means that the thickness is not changing. That means that the position of this reflection should not change too much. And that's how you can prove that this tracing is correct. In case if your thickness is changing dramatically, that means you got a huge geological differences between the points, and in this case you can start thinking that the black line is correct. And it's actually pretty much depends on the actual situation, on the actual field. In the end of the horizon tracing, you're going to obtain the map, but this map going to be in time domain. That's the isochrone map of a certain reflection horizon. The next step is how to trace the faults. The fault is once you got the horizon, originally it was connected, but then it was faulted by a certain reason, and now these reflections are not connected. Let's look at the example. In this example, I know that, let's look at the example. And this example, you can find out quite a lot of the faults disconnecting at different layers. That's how we can trace the main ones. But actually, you can find much more faults that is shown on that figure. And it starts the question, how many faults should we trace? How many faults should we find out on our seismic section? And the answer is, it depends on the task. Sometimes it is important to trace the whole of the faults, but sometimes it is a wise idea to trace only the main ones to save your time. The next important question is how to trace the faults between seismic lines. In case if you get 3D seismic, it's quite simple. You can simply trace the fault on one inline and then another inline and then the third inline, and that's how you can obtain the 3D picture of your actual fault. But what's going to happen in case of the 2D seismic? In 2D seismic, you get only seismic line and you get a fault. And if you look from above on that situation, this fault gonna looks like only a point. Let's look at the figure. That is the map of the location of the seismic lines on one of the fields. And by these red dots, it is shown the presence of the faults. The question is how to connect these faults between seismic lines. It's not an easy task, actually, because we can connect, for example, this point with that point, we can connect it with that point, or these faults are disconnected. We don't know. The only possibility is to connect that fault to any other variable that is not obtained from the seismic data. And this variable should present in all of the places, not only on the seismic line. In our case, we tried to use geochemistry, and we place the map of geochemical anomalies on the map of the seismic lines with the faults. And by looking at that map, you can simply find out which faults are actually connected and what's their geometry between the seismic lines.